Okay, everybody, welcome to the webinar on programming EyeLink experiments using Psychtoolbox for Matlab. So in this webinar, we're going to talk about a few different experiments that have been programmed in Psychtoolbox for Matlab that interface with the host PC and EyeLink eye tracker and allow you to do different things. We're going to get into a little bit of detail about some different aspects of this stuff. Okay, so in terms of an agenda for today's talk, first we are going to just very briefly discuss how you can find resources to get Psychtoolbox set up and working with the EyeLink system. I'm not going to get into too much detail about that because we have a kind of getting started sections of our form that covers that. But once we do that, we're going to start discussing how to program. So first, we'll go through a very simple example called EyeLink Picture, and we'll use that to just discuss very basic interfacing with EyeLink systems. Then we will kind of discuss in more detail some of the messages and types of information that you want to send from your script to the host PC to make sure that you have the information you need for data analysis in your data file. So we'll discuss that. Then we'll kind of shift gears a little bit and go to a more advanced topic of how to grab information like eye data from the host PC using your Psychtoolbox script. And that can be used for like gaze contingent studies. So people can use that for fixation monitoring online or for moving window paradigms, those types of things. So we'll talk about a couple examples that show how to do online access to the data. Then finally, we'll talk about how to draw custom calibration and validation targets. And this would show you a little bit, at least, about how kind of the structure of the EyeLink toolbox works. So I'm going to move on to the next slide here. So the first thing you want to do is make sure you have your display PC set up properly. So you got to install Psychtoolbox. I'll leave it to the Psychtoolbox guys in terms of providing instructions for that, but I'm assuming everybody knows how to do that. Then you need to install the EyeLink Developers Kit, and you can find more information about how to do that and how to get things up and running from this Getting Started section of our support forums. And I have it pulled up here. So if you go to like our main web page, then go down, we added this new Getting Started section. If you go in there, you can go Getting Started with Experimental Programming. And then down here, we have Getting Started with Psychtoolbox. And this just has some instructions on how to install and configure things so that things are working. I'm going to leave that information to this, and we're going to now jump right into the programming stuff. So first, let's just talk about a very simple example. And let me just show you. When you install the Psychtoolbox, if you go to Toolbox, that's your Psychtoolbox. Then go into the Psychtoolbox folder, then go to Psych Hardware, and then notice you'll see EyeLink Toolbox. So the EyeLink Toolbox actually comes with the Psychtoolbox, and if you go in there, you're going to see a section called EyeLink Demos. And when you go in there, you're going to see this section called SR Research Demo. So just to give you a little background, there are a couple other folders here called EyeLink Short Demos and Gaze Contingent Demos. These contain demos that were created by the original creators of the EyeLink Toolbox a long time ago. And we've kind of expanded on them, cleaned them up, and like made new demos that are kind of streamlined, have some more comments, and also that contain integration messages for our data viewer software. So if you use data viewer, it's great because they already are set up so that they'll produce data files that are friendly for the data viewer software. If you don't use data viewer, it doesn't matter because the communication with data viewer is all handled through these messages that basically log information to the data file. And the type of information that you would need if you were using Data Viewer is the same type of information you would need if you were not using Data Viewer. So it's a good idea to have that type of information in your data file anyways. And in other words, what I'm trying to say is it doesn't hurt to have Data Viewer friendly integration messages in your data file, even if you're not using Data Viewer. Okay. Anyways, so if you go in this SR Research Demo folder, and then you'll see from there, you'll see the file called EyeLinkPicture, and that's the one we're going to be working from. I've actually kind of taken all the materials that we're going to discuss today and put them in a folder here, just in my own special place. So you can do that type of thing if you want. And I put it in here. I'll just open this EyeLinkPicture. Okay, so now I have the EyeLinkPicture example opened. I'm just going to scroll up to the top. I already had it open. So we're going to come back and talk about this in a second. Let's just briefly talk about what this project would do if we ran it. It's going to first ask for the name of the data file. Then it's going to make a connection to the eye tracker. It's going to allow you to calibrate the eye tracker, and then it's going to start the loop of trials. And it's going to do 3 trials in this loop. On each trial, it'll do a drift check, then it will start recording eye data and draw the picture. Then it's going to wait for a key press or button press, and then it's going to stop recording and end the trial. And then at the end of all those trials, it's going to transfer the data file from the host PC to the display PC. Okay, actually, maybe we can try to run it. I don't know if it's going to show up on the webinar. Hopefully it's not going to mess anything up, but I'm going to run it, and you can raise your hand or ask a question if something goes wrong. But anyways, I'll run here. You can see it asks for the name of the EyeLink data file, the EDF file, and I'm just going to use the default demo, and hopefully you can still hear me. Now it's running. I don't know if you can see that, but this is what you would see on the display PC when you run it. And this is where you would do the camera setup. So you like focus the camera, do the calibration, all that kind of stuff. And then once, I'm not going to go through the calibration steps. You can check out some videos on our webpage about that if you want to learn more about calibration. But I'm just going to start the experiment. It goes to a drift check, target. I have the host PC in mouse simulation mode. So when they look at the target, we can press a key to start the trial. They'll see the trial stimulus, press a key to end it, see another drift check, trial 2, press a key, drift check for trial 3, and then trial 3 stimulus, press the key to end it, and then it will send the EDF file over to the display PC from the host PC. Okay, so that's kind of like if you ran the experiment, that's what the participant would see. Okay, a lot is going on behind the scenes. And it's not, none of this is really complicated, but this is what we're going to talk about today, is like what's going on behind the scenes. So if I scroll down here, behind the scenes, we are going to send a command to produce that little prompt that asks for the EDF file. Then we're going to do some normal Psychtoolbox functions to open a graphics window so that we can draw to the screen. Then we're going to send some graphics information to the EyeLink toolbox so that it knows like what our screen size is, for example, so that we can draw the calibration targets, which will kind of happen automatically once we go into camera setup mode and choose to calibrate. Then we're going to make a connection to the host PC and to the eye tracker and send some commands to tell it to open the data file. Then we'll send some commands to configure the host PC. Then we'll send a command to go into camera setup so we can calibrate the eye tracker. Then we're going to run the trials. And if you remember, we just kind of like presented a picture on each trial, but we were also sending a trial onset message, sending the trial number to the host PC so that it can be presented at the bottom right corner of the host PC so that the experimenter can see that number during the experiment. Then we put the host PC in an offline mode, send some information to the host PC about the stimulus so that we can see that as a background on the host PC, do a drift check, put the host PC back in offline mode, start recording, draw the trial stimulus, wait, and then send some messages to mark the occurrence of that drawing. That's super important. Then we wait for a spacebar press, and after that happens, clear the screen and send a message, stop recording, send some special messages that give interest area and trial variable information to the EDF for data viewer, then send a trial offset message that just marks the ending of the trial. And then we're gonna, after all the trials are done, send some commands to close the EDF and then send a copy of it to the display PC and then close the connection between the two computers. I've met with a lot of people that, and I've done a lot of technical support for people that use Psychtoolbox. And I would say, number one, I'm going to try to point out common mistakes people make during this process. Like, number one mistake, I think, is failure to do this, which is put the host PC into this offline mode before we start recording. If you do that, your experiment's going to seem to work fine most of the time, but every now and then you'll miss, the host PC might miss the command to start recording if you don't do this. So this is super important. Okay. Anyways, now let's go back to the script and see how these different things are implemented. Okay, so I'm just going to kind of walk through the script, and I'm not going to go into detail about every command, and I'm not going to go into detail about the comments, but basically this is the script that just presents a different picture on each trial. Okay, so as we go through it, first you're going to see that it just does some kind of clearing of the command window, all that kind of stuff, and then it checks to see if we're using Octave, which is like a free Matlab alternative. If you're using regular Matlab, don't worry about that stuff. Then you can see we set up a little list of the images to use on each trial. Excuse me. Then we set a variable called dummy mode. And if we want to kind of test our script without a host PC, then we can turn dummy mode to 1, and it will kind of basically kill the eye tracker functionality. So that's a way you can test it if you're like working at home or something. Okay, then we're gonna move on to step 1. And the comments in this script correspond to these different steps here, okay? So step 1, we're gonna put up a little dialog box that asks for the EDF file. And as I mentioned, I'm not going to go through every little line here. I think a better way to kind of interface with the eye tracker is just use one of these examples, copy this, paste it to your script. But if you remember the little EDF file dialog that popped up at the beginning, this is what produced that. Then we're going to create a drawing window here. This is actually just plain old normal Psychtoolbox stuff. So we're creating a screen here that we can draw to, and we're calling it window. That's important. So if we call it window, notice we're going to use that down here. So we call it window, and then in step 3, as I mentioned, we're going to send some details about our drawing environment to the EyeLink toolbox via this EyeLink init defaults function call. And when we call this function, it just gives information about our drawing window, which you can see we're passing here. And that allows us to do the calibration properly. Okay, then step 4, we're going to initialize the connection to the host PC. And this one just uses a little trick where we pass the dummy mode value, and that way it will kind of allow us to use dummy mode if that's set to 1. And basically you can see there's a classic programming trick, like basically if we run this and something fails, and it's going to give a little error message. Okay, then and so this is what actually makes the connection here in step 4. This is what makes the connection to the host PC. Okay, then after we do the connection, this section here runs a little EyeLink function called getTrackerVersion, which is going to return the version of the host PC software that you're using. And if you're using like a lot of different types of eye trackers with your same Psychtoolbox script, then you can use this function to check which type of tracker you're connected to, because maybe you want to do slightly different things for different trackers. But this shows how to do that. Then we send a command to the host PC to open that EDF file that we specified up here. So right here. So this is basically a variable that gets set from our little file name dialog, and then we tell the host PC to open that file. And if we have a problem, it'll just print these error messages and shut down. Okay. Then if you want, you can add a little header text to the EDF file. You don't have to do this if you don't want, but sometimes it's nice for record keeping. Okay, then this little section here is where you can see we're running this Psychtoolbox function called window size, which is going to return our screen resolution. And it's going to place the values in these variables width and height. This is important. Okay, so down here, after we grab width and height, we can send a command to the host PC to tell it to change one of its parameters. And this parameter in this case is called screen pixel coordinates. The host PC, for those of you, if you're familiar with the EyeLink system, you're already going to know this, but the host PC has a lot of parameters. Like some of them are clickable buttons in the host PC interface, but a lot of them are stored in INI files on the host PC. And this is an example of one that's stored in a file called physical.ini. And this is a parameter that tells the host PC what the screen resolution of the display PC is. Okay, so we're going to be like drawing things on the display PC monitor, and we're going to be creating interest areas around regions of that monitor. And we want the eye data to be formatted so that the eye data comes out in a coordinate system that is based on that same screen resolution. So if you used EyeLink before, you know that the eye position data is reported in pixels. So top left corner of the screen is 0, 0. I'm using 1920 by 1080. So the bottom right corner is 1919 by 1079. And this is just saying, okay, host PC, format your data based on this display PC resolution. Then, so that's important to do to make sure your eye tracking data matches kind of your screen positioning data. Then we're going to send a message to the data file. So this command sends a command to do something or to change a parameter. And the message, EyeLink message, is going to send a marker or some kind of just text message that's going to receive a timestamp on the host PC when it's received. So when we send a message, if you open the EDF file later, either in Data Viewer or import it directly into Matlab or make a text readable version, you're going to see messages. And the message is going to contain whatever message text you send here. And so in this case, you can see we're actually just writing a message that contains the same information that we sent for the screen pixel coordinates. This little message here is actually a special Data Viewer message. Let me just quickly launch Data Viewer and I have an example data file here. I'll just load this one instead. So when we launch Data Viewer, you're going to see a window here that allows us to see kind of what the subject saw and see the eye position data on top of it. And this display coords command message tells Data Viewer how wide and how tall to make this little window. So that's important. Okay, then we're gonna send another command that changes another parameter. And this one tells the host PC, hey, let's use a 9-point calibration routine. So if you're familiar with the EyeLink system, you know that there are different calibration types. There's 3-point, 5-point, 9-point, and 13-point. And this one is using the horizontal, vertical 9-point routine. So we're going to use a 3x3 grid of calibration targets. Then we're going to, through a series of 4 commands here, set file event filter, link event filter, file sample data, and link sample data. There are actually 2 sets of these right here, and we're only going to execute one. And if you trace this back, you can see we're actually just checking what tracker version we're using here. We're saving these variables V and VS, and we're just doing a little formatting here. And if we're using EyeLink 1000, 1000 plus, or Portable Duo, then we use these values. And if we're using one of the older EyeLink 2 or EyeLink 1 eye trackers, we use these old ones, these older kind of possibilities. But anyways, file event filter is specifying in terms of experimental events, what are we going to record to the data file? Link event filter is saying in terms of experimental events, what are we going to make available to our script in real time during the experiment in case we wanted to grab that information for something like a gaze contingent paradigm. So this link means the link between the display PC and the host PC. Okay, so whenever we see file event filter and file sample data, that means EDF file. And we see link event filter and link sample data, that means data available over the Ethernet link between the two computers online during the experiment. Okay, so in terms of the events that we're going to record to the data file, and in this case, make available over the link, we're going to record left and right eyes, fixation, saccades, blinks. That's the eye data we want. And then we're going to record any messages that are sent from the display PC, button presses, or if we're sending sync events directly to the host PC through the parallel port, like if you're doing maybe MRI study, sometimes you might have the MRI send a sync pulse, then that's what this input is. It's signals received by the host PC over the parallel port. Sometimes people ask, why do we have left and right? And that just means if the left eye is being tracked, let's record the data. If the right eye is being tracked, let's record the data. If you're tracking binocularly, you should always still leave it left-right because you're probably going to make the decision of which eye to track when you set up the participant. So basically always leave left-right there. Okay. Down here, we're specifying for each sample that is written to the data file, what are we going to record? And so by sample, I mean like, you know, the eye tracker is recording, let's say 1,000 hertz. Then that means 1,000 times a second, there's going to be a data point, like a sample in the data file that tells the eye position and the pupil size and the current time and some other stuff. So basically, this is saying for each sample, or 1,000 times a second and at 1,000 hertz, we're going to record data from the left and right eye. This is the position, gaze is the position data, or where on the screen in screen pixels they're looking. Href is like head referenced eye position angle. It's kind of like for, it's usually used in non-screen based eye tracking. So if you're tracking with a display PC monitor, tracking over a display PC monitor, you probably don't need this, but some people use this for non-screen based stuff. Area is the pupil size. H target is if you're in the head-free remote mode of the 1000, 1000 plus, and Portable Duo eye trackers, then this will record the position of the head target sticker, and it's going to record the kind of X and Y in arbitrary camera sensor units, and it's going to record the distance from the eye tracker in millimeters. Then gaze resolution is the number of pixels per degree of visual angle in the horizontal and vertical dimensions. And status is just like a flag if there's kind of a potential issue with the eye tracker, like if the participant is too close or too far in the remote mode. And then input is sync signals from other devices. And you can see we're basically making that same stuff available over the link as well. We just left out href. That's fine because we're actually not using any link data in this example. Okay, so we set that stuff up. This is important because if somebody has gone into your host PC and like changed settings, like clicked a bunch of different things, then these guys here in this section are going to make sure that everything is set up so that you're recording what you need to record for your experiment. Then we're gonna, this is another little command where we can say if we're using a button box that's connected to the host PC, like a Sidewinder or Xbox 360 controller, whatever button box is supported by your host PC, then you can use button 5 to accept drift checks and start the trial. Okay, So we're kind of doing some setup stuff here. Then we're just doing a little double check here to make sure that we're still connected to the host PC. Then we're going to check, or sorry, then we're going to configure the background color and the target color for the calibration. Okay, so this is RGB values, and this is kind of like a gray color here, and this is black down here. Okay, then we're gonna set up some parameters that control beeping sounds that are made during calibration. Personally, I cannot stand the beeping sounds, so I put these little comment in here, set the second value in each line to 0 to turn the sound off. If you ever see a script that I've actually used, I always have those set to 0. But that's a way to turn the beeps off. Then we have to call this little function here called EyeLinkUpdateDefaults to apply these changes. So if you just set these and then don't call that EyeLinkUpdateDefaults, then these changes don't get applied. Okay, then this section here, EyeLinkDoTracker setup, is where we actually calibrate the eye tracker. So this puts the display PC and the host PC into a special mode called camera setup. And this is where you're gonna like focus the camera, make sure the subject's positioned correctly, adjust the thresholds, and then do calibration and validation. And once everything looks good in terms of calibration and validation, if you remember, you can press the output/record button on the host PC or press O to start the experiment. And so basically after we've finished calibrating, we were going to press the O key, and then we'll start our loop of trials. Okay, this is where kind of the important stuff happens. And if you look up here, it says for I equals 1 to 3. So we're going to do we're going to iterate 3 times. This is our trial loop. And at the beginning, we're just going to grab an image file from that list that was way up at the very beginning of the experiment, up here, right here. So we're going to grab an image file from there, and that's going to be the one we're going to draw. Then we're going to send a message to the EDF file that says trial ID 1 on the first trial, trial ID 2 on the second trial. And I say 1 and 2 because this is coming from here. Okay, so this trial ID message is what marks the beginning of the trial for our data viewer software. And when you load the EDF file into data viewer, like when I load a test run through that, you can see how it divides the one data file that I've called test data here into 3 trials. And it does that because it reads these messages. And you just need to put a different value for each trial. Okay, even if you're not using data viewer, you still would want a marker like that. So still a good idea to put that in there. If you are using data viewer, it needs to follow this exact format. Okay, then we are going to send a command to tell the host PC to write on the bottom right corner of its screen during recording a little message. That's what this record status message is. It just draws a little message at the bottom right corner of the host PC in a little kind of bluish green box that in this case is going to say trial 1 out of 3 and then give the image name. So you can see this goes there, this goes there, and this goes there. And that's just to help us. It's totally optional. It's just to help the experimenter know how far into the experiment they currently are. All right, then I don't know if you remember, I said one of the biggest mistake people make is failing to call this set idle mode command. And this is what puts the host PC into a special mode called offline mode. And we're actually, in this case, we're putting the host PC in offline mode so that we can do some drawing to it. And in this case, we put it in offline mode and then we clear the host PC's background to black. So that's what this clear screen 0 is. And then we send the command to draw a little box on the host PC, and we draw it with these coordinates. And you can see it's basically a 100 by 100 pixel box that's going to be drawn in the center of the screen. And that's just to give us some landmarks during the experiment. And we're going to see the eye position move on top of this drawing stuff. So this is like a representation of what's going on in the display PC on the host PC. Okay, then this shows how to transfer the exact image that the subject's going to be seeing, and this copies it over to the host PC so that we can see the image that the subject sees with the eye position laid on top of it. Okay, then we do a drift check, and if you've done an EyeLink experiment before, you know that's just the simple target that's presented at the beginning of the trial. When the subject looks at it, either the subject or the experimenter presses the space bar, or in this case, button 5 on the host PC, because of this one here. And when they press that, it moves on to the next section of the script. And in this case, we put it back into offline mode. This is where it's super important. So we really want to make sure we always put it into offline mode and then give a brief pause of about 50 milliseconds before we send the command to tell the host PC to start the recording or start the eye tracking. So up until this point, we actually haven't even been doing any eye tracking. And when we hit this command, we start recording. But it's super important to make sure the host PC is in the offline mode before you issue that start recording command. And this is to make sure that the host PC does not miss the start recording command, which it will do a very small percentage of the time if you are not in offline mode, or which it can do, I should say. Okay, then after we start recording, we wait 100 milliseconds. And this is also important. This is basically to make sure that the host PC is up and running and recording properly before we do any trial drawing. Okay, that's important. We don't want to like start recording and draw at exactly the same time, because then we might miss the first few milliseconds of eye data. So we just wait 100 milliseconds, and then this section draws to the screen. And as you Psychtoolbox users know, this flip command is the one that actually does the drawing. And this flip command is like synced. Basically, the next line of code is going to be synced to the refresh, to basically the time when the computer sends the command to the monitor to update the screen. So it's what we would call like retrace locked drawing or something like that. So basically, whatever command we put next is going to be locked to within a millisecond to the time of the command of drawing to the monitor. Okay, so this little message here is super important. This is like our, I keep saying everything is super important, but this is also super important. This is the message that marks the occurrence of this experimental event. In other words, it marks the time when we draw to the screen. And this is going to be useful in data analysis because let's say like we do a lot of different things during a trial. In this example, we don't do this, but let's imagine we did a lot of different things in the trial. Then you could use different messages for each component of the trial. And then when you go to do the data analysis, you can use those messages to find the section of the trial that you're interested in. If you're using Data Viewer, we call that setting an interest period, and you do that up here in Data Viewer. You can see our Data Viewer webinars and videos to see how to do this, but basically you would use the message that marks the start of your period here and use a message that marks the end of the period there, and that will restrict the data that is being considered in Data Viewer. So this message that marks the experimental event is super important. And then right after it, we send a message that tells Data Viewer how to reproduce the trial stimulus. So up here, we draw the stimulus for the participant during the study. And this is just a message that gets stored in the EDF file. But when you load it up in Data Viewer, it's what allows us to see this image, in this case, like a picture of Quebec City, okay? And the fact that we can see the image here is due to this message here. Okay, I've kind of mentioned a few different messages that are particular to Data Viewer. In this PowerPoint, one of the slides that I put up here covers these messages, and I've kind of talked about them already. Really, the PowerPoint is just, you can get that later for reference of the different types of messages you want to send, but these are trial event messages that we send right after the screen update, and this is the image load message. And down here you can see that if you want more information about this formatting that data viewer needs, if you are using data viewer, then you can go help, contents, and then under protocol for EyeLink data to viewer integration, you can see like image load commands. This describes the formatting that's expected for for these types of image load messages. Okay, so this one is going to say we are drawing an image and we're drawing it in this is the position of the image. So basically you say image load, and then you say what's our positioning type? Is it fill the screen, position it so the top left corner is at this set of coordinates, or position it so that the center of the image is at the following set of coordinates. So if you're using top left, it'll position, like up here in this example, it'll position the image called fixations.gif so that its top left corner is at the coordinates 200, 200. If you use the center command, it'll position this image fixations.gif so that the center of the image is at 200, 200. And if you use fill, it'll just stretch the image to fill it to the screen. Okay, so we go back here. That's the image load command. Then we define a little key that can be used to end the trial. And then we do a little programming trick. It's like a perpetual while loop. So basically this while, it's kind of like saying while true, which will make it just loop forever until you hit a break. Okay, so we're entering a loop that'll just loop and loop and loop and loop until you hit a break. And on each loop, it checks to make sure we're recording still. And maybe the experimenters pressed a button on the host to kill recording. If so, then it breaks. Or if a button is detected on the EyeLink button box, if you have a button box connected to the host PC, then it'll, when it detects a button press, it'll write a message to the data file and then break. Or if it detects a space bar was pressed, it'll write a message to the data file and then break out of this loop. After we break out of that while loop, we're going to clear the screen and then write a message blank screen. So this would be like our end of interest period message in data viewer if we were setting an interest period. Okay. Then we're going to stop recording for the trial. And after we stop recording, we're going to write some interest area information. You don't have to do this. This is another data viewer communication trick. And I think like the choice of whether to write interest area information directly to the data file or to instead use these drawing tools in data viewer, I think that choice, really there are two options. You can like send interest area information to the data file or to an interest area file and then have data viewer load that, or you can draw these interest areas here. And I think the choice depends on the type of paradigm. So if you're doing like a reading study, or sorry, if you're doing maybe like a visual search study, for example, maybe your Matlab script is going to draw like 100 L's on the screen at random positions, and then there's going to be like 1 T on the screen at a random position. And in your Matlab script, you already know those positions. So you might as well go ahead and write the interest area information to the data file, because otherwise it would take forever to redraw those interest areas in data viewer using these. But if it's a picture experiment, then you can use these and just draw your own interest areas, and you can learn more about data viewer about that. But these little guys here, these kind of orange boxes, and there's one here and here, these are the interest areas that come from these little messages. And so these need to follow the formatting in the same EyeLink protocol under the interest area information. Okay, so you basically want your interest area messages to look like this in the data file. And the formatting is ID, left, top, right, and shape, ID, and then left, top, right, and bottom boundaries for rectangle and ellipse interest areas. And for freehands, you just put a list of coordinates. And if that's in the EDF file, when you load that EDF file into data viewer, you'll see those interest areas and you can use them for your analysis. Okay, then going back here, we write some more messages, and these are trial variable messages. And in this case, we're really just writing the trial number and the trial image file, but these are messages that also go to the EDF file. And when you load the EDF file, they become special columns you can include. It actually renamed it here because it has a built-in variable called index. Maybe I should have chosen a better name, or whoever made this should have chosen a better name, because in full disclosure, I didn't make this example. But anyways, you can see them down here in blue. They become variables that you can output along with any of your eye position data in any of the reports that you create. So those variables kind of become user-defined variables here. And you can also check their values using the trial variable value editor. Okay, so this is a way we can keep track of condition information or like any other independent variables that you're manipulating, or dependent variables. In this case, we don't have any dependent variables, but we could have like a reaction time maybe, and you could like send trial var RT space 328 on if the reaction time was 328 milliseconds. Okay, so these will pass variable information to the EDF, and then we send a little message that marks the end of the trial here. Okay, then this is the end of our trial, of one iteration of our trial loop, and it's going to do the other two trials. And then after we do all those trials, we're going to send a command to go back to the offline mode, close the data file, and then copy the data file from the host PC over to your current working directory, your current directory in Matlab. And then it's going to shut down the connection. So that's like the basics of the interfacing. And you know, let me just say, there are lots of ways to program experiments. You know, Psychtoolbox, Experiment Builder, ePrime, these types of things. I like Psychtoolbox because I feel like it's very explicit. Like everything is very clear. You can see the order of operations, and I feel like if you follow these examples, you kind of can't go wrong. Okay, so that's the basics of it. Let's go back to the PowerPoint. So this slide just summarizes all those things we just went through, all those different types of messages. And again, you can also look in the protocol for EyeLink data to viewer integration. Now let's, unless anybody has any questions, let's shift gears and start talking about grabbing eye data online. Okay, so grabbing eye data online means from the display PC in your Psychtoolbox script, you can send a command to the host PC to get current eye position data or to get eye position data. And there are really two techniques of doing this. And sometimes one technique is better, sometimes the other technique is better. But the two techniques, let's call them the newest sample technique and the buffer data technique. Okay, so the newest sample technique, this one up here, it's where you make a call to grab the most recent eye sample from the host PC. And that eye sample is going to include the X and Y coordinate of the eye, the pupil size, all those things that we specified in our link sample filter up here in the script. Or sorry, link sample data. And that newest sample technique is useful for something like a moving window paradigm. So like this is where you have like a window maybe that's clear and that is centered around your current eye position. As you look around, like you update the screen so that that window is always centered on your eye position. And so that inside that window, maybe it's a clear version of the image, and outside the window, it's a blurry version of the image or something like that. It's also useful if you just want to do something simple with the sample data, like check if they ever looked outside of a fixation window or something. Let me mention a couple kind of critical points. This newest sample technique only gives you the sample data, which is like position and pupil over time, position of the eye and pupil over time. Buffer data will give you sample data and eye event data, meaning fixation and saccade, start and end markers, that kind of stuff. But if you're using the newest sample technique, you're only going to get sample data. And let me also mention, these eye trackers sample pretty fast, so up to 2000 Hertz. So that means if you don't call this function, like let's say you're doing moving window paradigm and you're trying to update on every screen retrace, like if you don't call it fast enough, you might miss some data. So really this newest sample technique it's not the best choice if you're trying to grab every single sample over the link. Okay. All right, the second technique is called getting buffer data. And this is, as I mentioned, this is useful when you need to grab all sample data and or when you need to grab eye event data, because this technique up here, newest sample data, doesn't return eye event data. And basically the buffer data places all sample data and all event data like fixation, saccade, blink, button presses, input, those types of things are event data. It puts all of those in a buffer, and then you kind of grab those from the back of the buffer. So you're not grabbing the newest one in the buffer, you're grabbing from older stuff in the buffer. And this way, you're never going to miss anything because it's just a matter, you need to call it more, but you're always reading from a buffer, so you shouldn't miss it. But in either case, you should be programming. You're gonna set up these calls to get newest data and to get buffer data probably in a loop, and it's important to keep your programming efficient so that the loop is going to occur as frequently as possible, even if you're doing buffer data, because a lot of times you want to do something like calculate your own ongoing velocity, which requires like all the eye data usually if you're using the technique we use, and if you want to get the most up-to-date version of that kind of moving window of eye data, then you're going to have to call this function a lot, okay, and frequently. So let's go through a couple examples. Let's first talk about the newest sample technique. So I'm going to open up, I have in my little folder here, this one called EyeLink Fixation Window. Okay, and if I open that up, I'm not going to go through all the details of this, but basically on each trial you see a fixation target. The participant sees a fixation target. After it's shown, there's a 200 millisecond, after the target first appears, there's a 200 millisecond grace period, and that gives a participant a chance to move their eyes to the target. But then after that grace period, for the remainder of the fixation period, the participant must maintain gaze position on the target. And if the gaze position is maintained throughout the whole fixation period, they're going to see this smiley face. And if they break fixation, then get that one. Okay, so it's kind of a cute little example. But anyways, this example uses the newest sample technique. This EyeLink fixation window uses the newest sample technique. And I'm going to skip through all the kind of initialization, and let's just jump right into the part of the script that does the trials. So if I scroll up here, this is where we start recording on line 249. And if right after we start recording, you can see we call this function EyeLink eye available, which is going to return a 0 for left eye, 1 for right eye, or 2 for binocular. And this is just saying we're only going to do this fixation window based on one eye in this example. You could easily set it up to use both eye data, but in this example we use one eye. But this is saying if we have binocular data, let's just use the right eye. Okay, so we do that there. Then we draw the trial image, and then this is just one, I'm going to ignore this for now. Let's just go right down to here where we start our little loop. This is the critical part. So this is where we set up this is the fixate time is going to be how long do they have to fixate on the fixation cross to get the happy face. And then the grace time is like how much time do they get at the beginning of the fixation period to get move their eyes to the target. Okay, once we set these variables, then we're going to start a little loop that's going to go until our current time is greater than the fixation time, greater than or equal to the fixation time. So as long as our current time is less than the fixation window, we're going to make sure we're still recording this little section here. If we are still recording, then we're going to run this function EyeLink new float sample available. Okay, so let's go back here and just talk about the logic. We're going to check to see if there's a new sample available. That's what this is doing. Is there a new sample? So if you have a like super fast script or you're going at a low sampling rate on your eye tracker or something, then maybe there is not a new sample since the last time you checked it. And so this is just saying, let's make sure we're not recycling old data. And so let's say, is there a new sample? If there's a new sample available, then let's grab it. And this little guy here, EVT equals EyeLink newest flow sample, this is where we grab the newest sample and put it into this variable called EVT. Okay, these little things here are kind of leftovers. So this actually just writes it to the command window, writes the position. Okay, then you could take that out. Then we're going to check, do we already know which eye we're using? Which we do because we just talked about that. And if we do, then let's say X is going to be equal to the gaze X component of our EVT data structure. And Y is going to be equal to the gaze Y component of the EVT structure. And you can see we passed the eye that we're using there. And we just add 1 because in Matlab, the arrays, the indexing starts at 1 rather than 0. Okay, then we just make sure we don't have missing data. It's going to have missing data like whenever the subject blinks or tracking is lost for some reason. So like if the subject just walks out of the room, then you're going to still get samples, but it's going to have missing data for the position. And so this is saying, let's make sure we're not in a blink or have missing data. And if we have legitimate position data on the screen, let's save that to variables mx and my. So mx and my are the actual eye position data. And after we run this little set of commands, and this is like if you're using a mouse version of it, like a kind of mouse simulation or something. But if we're not doing that, then, and we're using the eye position, then we're going to go down here and say, if, all right, so this little thing is calling a function that's another place in the script that checks to see if our current position is inside a window. Let me just check. I think it's at the very end of the script. Yeah, down here. This just checks to see if our current eye position is inside some fixation window that we've defined. Okay, that's defined elsewhere in the script. If it is, and we currently, or on the previous iteration of the loop, we're not in fixation. So I didn't point this out yet, but there's a variable up at the very top called infix that we set to 0. And you should set that to 0 at the beginning of each trial. Then if we are currently inside the window and we previously were not inside the window, then we're going to say, write a message to the data file saying this is the start of the fixation. We're going to set the variable called infix to 1, meaning we are now in the window. If these two things are not true, then let's check, are we now outside the window? And previously we were inside the window, and we're currently past the grace period. If these are all true, if we're outside the window, if we previously were inside the window and we're outside the grace period or past the grace period, then we're gonna we're gonna clear the screen or draw the frowny face and then write a message to the data file that says this, okay? So this loop will just keep going, or if you can press a key here to end it there. But this loop is going to keep going until our fixation time period is up, and then we're going to end here. Then after the fixation time window is up, if we still are inside the window as recorded by our infix variable, then we're going to draw the happy face. And we probably should have put a little message there to mark that too, but you get the general idea. Okay, then we're going to stop recording and then write, you know, in this case, it's a little bit weird. We write the image load here commands, but usually you would want to put that right at the beginning of things. But we're basically, sorry, let me clarify what I meant there. I kind of trailed off. Usually we want to put the image load command right after the draw, the flip command, but in this case they do it later. Or actually, sorry, they do it here. Then we write some messages, etc. So that you can see in this case, we're just checking to see if if there's a new sample, and if so, grab that sample and just check if it's inside the window. Okay, so that's the first technique. Okay. And this works for moving window. This works for simple fixation, like window checking, something like that. Now let's go on to the second trick, which is the buffer data technique. Okay, and this is going to illustrate like how to monitor for the current gaze position. In this example, change.m, it's going to use this buffer data technique to show how to monitor the current gaze position and detect the deviation. So it's using kind of the same, you know, technique as the other one, but in a slightly different way. We're using buffer data. So on this one, on each trial, it shows a flickering chessboard. This is kind of like change detection. So the chessboard is going to flicker, and on each flicker, one of the pieces is going to change. And if the participant gets 300 milliseconds of consecutive fixation time on that changing piece, then the trial is going to end. And in this case, fixation time is based on something called a fixation update event. And this is something that the host PC does every 50 milliseconds by default during a fixation. It's going to send, or basically add to the buffer something called a fixation update event, which is going to record the current average X and Y position of the fixation and the time and some other information like that. And so this is saying, like, this experiment is going to check that those fixation update events, and if we've accumulated 300 milliseconds of consecutive fixation time as indicated by our fixation update events, then we're going to end the trial. Okay, so let's open up that example. I'll go up into my materials here and go to the change example. This is in that same folder that I mentioned at the beginning under Psychtoolbox, Psych Hardware, EyeLink Toolbox, EyeLink Demos, SR Research Demo. You can see these same examples are in there, but I'm just opening it from here. And it looks like I've already scrolled down to the section where we do the looping. So in this example, let me scroll up just a little bit. We're checking which eye is, we start recording, check which eye is available, and then down here, we start a little loop that does the flickering. So we're going to be drawing this stuff, drawing the the chessboard, flickering between the two images. But down here is where the critical action happens. And so this is where you would create your loop to be grabbing data from the buffer. Okay, and in this case, we just need to grab 30 should be plenty because we're just kind of grabbing the data from the buffer, like on each flicker. And basically what we do is say, let's call a function get next data type. And what this does is tell us what the next item, what type the next item in the buffer is. So we're creating a little buffer on the host PC, and each item in the buffer could be a sample, it could be a start of fixation, it could be an end of fixation, it could be a fixation update, it could be button press, lots of different things. If you want to see kind of like a full list of what those things are, then you can actually go to the EyeLink Basic and go to EyeLink Init Defaults, And if you scroll down, you're going to see here are some of these types. You can see, okay, sample type equals 200. So if that function returns, if that function, if that function getNextDataType returns 200, then it's a sample type. And so we've defined these kind of constants here, and you could either say if event type equals fixation update, el.fixUpdate, or you could say if event type equals 9. So the value that's returned by this getNextDataType is going to tell you what type of data is next in the buffer. And it could be a start of a blank, end of a blank, start of saccade, end of saccade, all these different types. In our example, we're only interested in the fix update types. So if the type is this, then we're going to grab the data, grab the actual data using the get float data. In another experiment, we might want to grab sample data. So in that case, we would check if event type equals 200 or equals el.sampleType. But in this case, we're just trying to search for the fixation update events. And when we find that it matches, then we grab the data. And when we grab the data, in this case, we say only do this if it matches the eye that we use, because like we could have a start saccade for the other eye that we're not interested in. So we're going to make sure that the eye component of the data that we grabbed is the data is being saved into EBT. We're going to make sure that the eye component is matches the eye that we're trying to use. Then if it does, we're going to write a message that just gives the fixation, that writes the fixation update information to the EDF file. And then we're going to say if in fixation window, so we're going to check to make sure that we're inside that window, and we're going to pass to our little function that checks this, where the size of our window and then like the position. And if it is inside that, this will return a yeah or 1 or something. Then we're going to say our total fixation time is equal to the previous total fixation time plus 50. And if the total fixation time is greater than or equal to 300, then we're going to break out of this. And if not, then we're going to reset the total fixation time to 0. And you would just keep doing that stuff in your loop. And you can imagine in cases where you need to grab every sample, then you can use this trick. Let me mention, actually, I'm going to even put it in the PowerPoint. I'm going to say it like this. You should make sure to start the data grabbing loop before your trial stimulus, usually, if you're trying to get every piece of data that happens while your stimulus is on the screen. Then you would actually start the loop, and then inside your loop, if it's the first iteration, or sorry, if it's like the 200th iteration, then you can draw the trial stimulus or something. Basically, what I'm trying to say is like start the loop of grabbing the data, and then after 100 or 200 milliseconds or so, then draw the trial stimulus. And this ensures that you are already grabbing data when your trial stimulus appears, and you're kind of like caught up to the buffer, to the latest stuff in the buffer that you're going to be able to get. Okay. Does anybody have any questions about that? Okay, it's kind of funny to do a webinar because I'm just by myself and it feels like there's no feedback. But basically, that is the idea. You are checking the next type in the buffer. If it matches the type we're looking for, then grab it and do something. And we just put all that in a loop. And in a proper kind of thing where we want to be grabbing the entire time we present a stimulus, we would also put our stimulus presentation in this loop. This example doesn't exactly do that, but you would want to do that. Okay, now let's shift gears and talk about using custom calibration and validation targets. Okay, so this is a little bit different than everything else we talked about. This is kind of changing some of the drawing components of the EyeLink toolbox. So I'm not sure if you could see the demo when I ran it at the beginning, but basically it just draws like calibration targets on the screen when you calibrate the subject. It just draws by default a circle with a little dot in the middle, and that's the default calibration target. But sometimes people want to use different types of calibration targets, and you can do that actually pretty easily. So let me mention let's go back to our Psychtoolbox folder. So I'm just going into Psychtoolbox, Psych Hardware, EyeLink Toolbox, and then you see here EyeLink Basic. This is where actually a lot of the functions that are used. This is where the functions that are used by the EyeLink Toolbox are defined. And you might notice there are two versions of this little guy here. This one called Backup is the original one. And actually I would want to, if I want to make sure it's not going to be used at all, I would give it some other extension. But in this case, I just want to open it, and I want to show you, this is the original, let me just move that. This is the original, I went the wrong way. Psych EyeLink dispatch callback. And if we scroll all the way to the bottom, I was already scrolled to the bottom. If we scroll all the way to the bottom, you're going to see this function called EyeLink draw calibration target. And you can see this actually just uses normal Psychtoolbox commands to draw the target at the location specified by this little 2-item array, which is just X and Y position. X is 1 and Y is 2. Okay, and so if you want to do your own drawing, you can just change this EyeLink draw calibration target that's in the Psych EyeLink dispatch callback. Okay, so I've already done that, and I have created a new file called Psych EyeLink dispatch callback, and you can see I have edited the function here, and I say if this variable called use custom target equals 1, then we're going to draw this. Else, we're going to draw, this is the same that was in the previous one, we're going to draw the default targets. And so this thing here is drawing our little custom target, which is basically drawing an image that is specified in the variable el.targetImage. So it's just drawing an image file instead of our target. Okay. Let me point out though, this variable here called use custom target and this variable here, these are not part of the EyeLink toolbox, this variable el.targetImage. And so we have to create, so what I did here is like, let's say I am trying to draw custom calibration targets in my experiment, but I don't want to disrupt the experiments of others who use the system. So I want to just create a variable in the EyeLink init defaults. This is the same one that defines like the event types that we talked about before. We can also create a variable in there called el.use custom target, or call it whatever you want. It doesn't really matter. But I chose use custom target. So if we go to my EyeLink init defaults, you can see I've defined a variable. And I just kind of put it with some other calibration stuff called use custom target, and I set it to 0 by default. So that way, if somebody makes a script and they don't specify el.use custom target at all, then when their program is doing the calibration, it's just going to use the old normal default calibration drawing. But if you want to do your own drawing, then in your script, you can set use custom target to 1. So I have made like an edited version. Sorry, let me go back to folder. I've made an edited version of EyeLink Picture called EyeLink Picture Custom Calibration Target. And if I open that up, we can scroll down and we can see down here, this one, defines 2 extra variables. One is called EyeLink target image, which is just specifying a little variable I have in here. or sorry, a little image file that I have in here called my target. And it's saved into the variable EyeLink target image, EL target image. And then I specify EL.use custom target is 1. If this is left off, it'll use the default calibration target. But if we add this, then it will use our custom target. So I'm defining a custom target and its path here. And I'm saying, let's use it. And that way, every time you run a calibration and it gets to this place where it needs to draw the target, which will kind of happen automatically, it's going to say, okay, use custom target is 1, so let's do this version of the drawing. And that'll do the default, that'll draw the special calibration target. Let me show you the calibration target. It just looks like this. And I use the same background color as the, so I put a little star there, on the same background color as the calibration screen, which was 128, 128, 128, as defined somewhere. Oh, wrong one. Right here. Okay, so if you want to draw a custom calibration target, you can, and not affect anybody else's stuff, first in EyeLink init defaults, add a line that looks like this. Second, in your script, before you call this EyeLink update defaults, set it to 1 and set some other variable that might define what you're going to draw as your calibration target. And then finally, in Psych EyeLink dispatch callback, down at the very bottom, just change the function to look something like this, so that if use custom target is 1, draw your target, otherwise draw the default target. Okay, so that's how you do a custom calibration target. So that's all I had for the webinar today. I'm going to post all these materials onto our forums at the webinar, at the same webinar thread where you saw the announcement about it. So if you want to get any of these scripts later, you can always get them from there. If you want to get the PowerPoint or the video of this webinar, you can get it there. So unless there are some questions, that's all I got. Thanks a lot for attending. Okay, I guess no questions, so let's say that's the end. Thanks again, and if you have other questions, you can also write to support@sr-research.com. I'll just write it out here. All right, thanks again, and good luck with the Psychtoolbox coding.